Let's take a look at some patterns where we have to describe multiple relationships at the same time. Supposing I want to find all of the directors that a particular actor has worked with. You can imagine this example being extended to a fraud case where we're looking at what accounts is this user associated with. Let's first create a query that won't work, so we can discuss it. Let's match all actor nodes where the name property is George Clooney. And we want to find all director nodes that have a relationship to that actor. Let's give them the alias of D, and let's return A and D nodes. Again, limit 25. As we suspected, that won't work, and we know why because we looked at a similar example earlier. Actors don't have direct relationships with directors. They are related via movies. The double dash that we've used here represents a single direct relationship, and so we get no results. So instead, what if we go back to our query, and after that initial relationship, we add any intermediate node, and then another relationship. So now we're defining the scope as actors named George Clooney who have a two-step relationship with a director. Let's see what happens. So we get 17 results here, one of which is George Clooney himself, and the others being directors that he's worked with. But we're still not seeing the relationships between them. And that's because of the nodes returned, A and D, which represent the actor and the director, there are no direct links. So in order to see those relationships visually, we're going to have to assign an alias to this middle node, which we'll call M, and we'll return that in our return statement. Because direct relationships now exist between the returned nodes, that's why we see the relationships. We expand this result slightly and zoom in. We can see all the movies that George Clooney worked on, and in addition we can see all directors that also worked on those movies. What we're also seeing though is some people that acted in movies, and we're seeing that because Hugh Laurie is also tagged as a director. Sure, he didn't direct this movie, but he is a director. He just happened to act in this one. So there's maybe some ambiguity in the question that we asked. Are we interested in any director that worked on the movies George Clooney was in which case this is the answer? Or are we interested in directors that actually directed those movies? In which case we need to get rid of the acted in branches and keep only those people who directed these movies. I'm going to go with that approach. And so in the second relationship where we have a director relationship to a movie, I'm going to add the square brackets in there and add a label condition to this relationship. This label must be directed. And so rerunning that query, we remove all the acted in relationships and leave ourselves with only the directors of these actual movies. You can start to see the use cases here for something like contact tracing or association. In the last video, we tried to find a very explicit two-step relationship. We defined the starting node, a relationship to a movie, and then a second relationship to a director. But suppose instead we just wanted to find all nodes that were two relationships away from George Clooney. We can use a more general notation to do that. So we match, again, an actor node. We define the name property as George Clooney. Close those brackets, and this time when we define the relationship, inside we place *2, for example, which means two hops or two relationships. So now this query is saying, find all of the instances where we have nodes that are two hops away from George Clooney. Let's see what we get then when we return n with a limit of 25. And remember, n are those nodes that are 2 hops from George. So we've got a few different types of nodes here. We've got actors, users, genres, but crucially we don't have the movies, because the movie is only 1 hop from George. What's interesting though is that George Clooney himself is returned as one of the results. Now we said we wanted to return n, which was nodes that are 2 hops away from George, so why are we getting George as a result? Have a think about that and we'll explore in the next video. The question I left you with is, why does George Clooney appear as a node 2 hops from the George Clooney node? To understand that, let's try and better understand the rules that apply when we're working with multiple hops across a graph. Take this super simple graph example with only 4 nodes. There are 3 nodes 2 hops away from A. We have B, C, but also A is 2 hops from A. And that's because we have 2 relationships there. We can go down one and back up the other, as long as we haven't restricted the direction in our query. But how many nodes are 2 hops from node B? Well, in that case, we just have node A and node C. So why isn't B 2 hops from B? Well, we cannot use the same relationship more than once. So we've learnt 2 things here. When matching a pattern in a graph, relationships can only be used once. And when matching a pattern in a graph, nodes can be traveled multiple times, as we saw in the first example. We started at A and we finished at A. So this is why George Clooney appears 2 hops from George Clooney, is because he must have both acted and directed in the same movie. If we wanted to remove George from the results and leave us with what we consider to be truly 2 hops away, we could apply a simple where statement to our query. Before the return, we could simply say where A is not equal to n. And so we're saying, when we match this pattern, if you find any instances where n is actually the same node as A, we do not want to return that. And so this time, we remove George from the results. Until now, we focused on nodes and relationships that meet a specific pattern. And primarily, we've been returning those results in some sort of graphical form like this, which allows us to explore the data. What if we want to know something about each of these returned nodes? What if we want to know the number of movies that each of these directors has directed? Or what if we want to know the average IMDb rating of films that each of these people has worked on? So now we get into the world of returning, counting, and aggregating properties. As an example, let's define a new scope as all movies from 2016. So match movie nodes where m.year equals 2016. And this time, instead of just returning m as we would have done previously to get those nodes, I want to return some properties. So return m.title and m.imdb rating. That instead gives us a tabular result. Careful again when you write these property names, because they are case sensitive. If I write IMDb rating all in lowercase there, we can see that the query still works, but I'm getting nulls for all the IMDb ratings, because there's no value assigned to a property with that name. So we need to make sure we keep IMDb rating with a capital R, as we see in the property keys list. Now, just like in SQL, we can return our results with an alias. Instead of these ugly titles, we can write as title, and for the rating, we can write as IMDb rating. And that will give us a cleaner looking table. But note that you can't have any spaces in these aliases unless you write them in quotations. So there we have a way of drawing information from the returned nodes and displaying it in tabular form. This is going to allow us to aggregate results and rank our table according to a certain condition. This will help us define which nodes or which results are the most important from the ones we've returned. In the last video, we looked at how to return the properties instead of the nodes. And just like in SQL, we can apply certain functions to those returned values. So here we're showing the IMDb rating to 1 decimal place, and for example, we could apply a round function to that, use the rating as the first argument, and round it to 0 decimal places. So when we run that, we get a rounded rating to the nearest whole number. Now, I don't propose to show you every function that you can apply to these numbers, and obviously you know that certain functions can only be used with certain data types. I will provide a list of common functions in the student documents, but just know that you can manipulate the results like this if you wish to. Now that we're seeing our results in tabular form, it's a bit easier to see these scenarios where we have null values in our results. And so let's quickly revisit one of those conditions where we specify that the rating must not be null. So again, starting from that previous query, I'm going to move the where clause onto a new line. I'll use an AND statement, and this time I want to say that m.imdb rating is not null. And just a reminder that because a null isn't really a value that we can compare with an equal statement, we have to use this is null or is not null syntax. Now we get a list of movies, but we only get movies that have a rating. Now that we know how to return the properties of nodes, let's have a go at ordering the results to get a sense of importance or ranking. Let's match all movie nodes and return m.title as well as m.released, which will be the release date, and let's order those results by m.released. And it helps to specify which order we want those to be arranged, ascending or descending. So let's do descending to get the most recent first. We seem to have a few null results there for our release dates, which are just movies that don't appear to have a release date in the graph. Others lower down do, so let's use what we know about dealing with nulls to get rid of those. Going back to the previous query, we're just going to add that where clause in, and we're testing the condition whether m.released is not null. You may also come across a different function called whereExists, although this function will no longer be supported by Cypher in the future. So I recommend you use the isNotNull approach. So doing that, we remove the nulls and we get our ordered release dates from the most recent going backwards in time. Notice here that we've got 3 movies with the same release date, but the titles aren't in any particular order for those 3. So what if we wanted to sort our results by 2 columns? First, the release date, and within each release date, let's sort the titles alphabetically. So to do that, we can simply add another item to our order by clause. So order by m.released descending, comma, m.title ascending, ASC. So now the dates are ordered starting with the most recent, but within any matching dates, we have an alphabetically sorted list of movies. So there's an intro to sorting the results that we get in tabular form. And obviously the benefits of sorting and ranking are endless. They allow us to pick out the most important items in some sense, or just give our results some sort of structure to make them easier to browse. And before we finish up here, I just want to show you one more thing with this same query. So pulling up that last one, something you might be used to doing in SQL is skipping the first few results. And so once we've ordered our results like this, perhaps we decide, for whatever reason, we want to skip the first item. So let's just do skip 1, and then let's limit 5. So we should have now 5 results, but excluding that first date that was previously in the table. In the next couple of videos, we're going to take a look at how to count certain elements of our results. The query I'm going to use to demonstrate this is the count of movies from 2016 produced per person, whether they acted or directed. So since my results are going to be ordered per person on the left-hand side of my table, to me intuitively it makes more sense to start my query with that node. So let's create a person node that has a relationship to a movie node. We've said the year must be 2016. So m.year equals 2016. And so in terms of our returned results, we want to first return a list of names. So p.name. The second thing I want to return is a count of the movie nodes, m, and let's return that as num movies. Finally, let's order by num movies descending. So it looks like Idris Elba was involved in 4 movies, Ben Foster in 2, and so on and so on. But there's one more complexity here that we're not capturing in our query. To explain this, scroll down and take a look at how many movies Ben Stiller is involved with. He's involved in 2. With that in mind, let's modify our original query and visualize it as nodes to see what those 2 movies are. So instead of returning all these properties, all I'm going to return is the p node and the m node, and I'm going to put one condition within my person node that name must be equal to Ben Stiller. And with that, I can return my graph. The problem is there's only one movie. So why was our query telling us that Ben Stiller was involved in 2? Take a look at the first query we created and have a think about what might be going on here to create this result, and we'll explore in the next video. The duplication in our results is a classic case of count versus count distinct, which you've probably come across before. But before I explain that, it's important to understand what the match statement is doing. And again, to do this, let's look at this basic graph. We've got 3 actor nodes and 1 movie node. So with this example count query on the right-hand side, we're saying set the scope using match to actor nodes that have name A that have a relationship to a movie. What the match statement is doing is it's finding all occurrences in the graph where that pattern is found. And that pattern is actually found twice. A and the movie have a relationship through acted in, but they also have a relationship through directed. So both of these patterns match what is being asked for in the match statement. The return statement is summarizing what we have in the match statement. The count function returns the count of movie nodes in those matching patterns. In my opinion, this is one of the keys to getting your head around graph databases. The match statement is looking for patterns that match. The return statement is simply summarizing the results in some way, and so the count of m in this case is 2. If we truly want to know how many unique movies actor A has been involved with, we need to use a count distinct to return the correct answer. Let's have a go. So we've got this query which is returning these 2 nodes, Ben Stiller and the 1 movie that he both acted and directed in 2016. So instead, let's return p.name to get it back as a list, and let's start with the count of m as num movies. And as we know, this is going to give us 2, because we have 2 matching patterns that fit this statement. one via directed and one via acted in. We know that that result is incorrect, and so instead we can add a distinct within that count statement to only give us unique occurrences of M, the movie. So now we just get one result. And so finally, we could even go and remove the name condition to give us the full list of people and the movies they were involved with. So let's just add back in the order by clause, num movies, descending. And so these are now the correct results. If you haven't quite grasped that concept of what the match statement is doing, obviously go back and watch the last few videos. This is one of them. This is where conceptually graph queries are a little different, but with a little practice, you'll have these queries down in no time. There's a couple of other ways that we can summarize the matched patterns within our query. The first of those is to return the count of matched patterns. And so for that, I'm just going to go back 2 queries to the one where we restricted it to Ben Stiller, because we know how many results there should be. Instead of returning these properties, I'm simply going to return count star, and that will give me the count of matched patterns. As we know, there are 2 patterns that match this, and so the answer should be 2. A different way that you might see these patterns expressed in queries is that the pattern is assigned to a variable. So we could create a variable called pattern, which is now equal to everything that comes after it. And so instead, if I count pattern, I will still get the value 2. And so this is just an alternative syntax that you might see in those match statements. In the last video, we explored how we could count nodes, count relationships, and patterns, which was really helping us to aggregate a set of results and draw out some sort of grouped summary from it. So I want to continue with that to show you a few different aggregations. This time we're going to start by creating a list of users and by counting the number of movies they've rated. So the scope we want to create using a match statement, first we want to find all user nodes that have a relationship of type rated to movie nodes. I only want to return results where the rating, so r.rating, is not null. And I want to return the user's name. And I want to return the count of movie nodes as movies rated. And let's order those results by movies rated, descending. So that gives us our starting point. I'm getting an error there which is saying variable r not defined. And the error is occurring within the where statement. So let's have a quick look back at that. We're saying where r.rating is not null. And actually it's because we haven't defined an alias for that relationship in the middle, so there was no r to refer to. So let's just put that in r. Run the query, and there we've got our starting point of list of users ranked by the number of movies they've rated. And so that's simply copying the method that we used in the previous video. We're counting the number of related nodes. Now, if we click on the rated relationship type on the left, just to see a few examples, and hover over one of them, we can see in the properties on the right-hand side that it's not just telling us that the user has rated the film, it's actually telling us the rating that they gave us. So that's a property of the relationship. So let's go back to the second last query that we ran and press Ctrl up twice to get back to that. So first we've returned the user name. Because we've used a count aggregation here on the second one, we're effectively grouping by username, and we're saying for each one, count the number of movie nodes. But now we've got some additional information that we want to get from each of the relationships. Now this result needs to be aggregated in some way, and so perhaps an appropriate way to summarize this is to say, well, for each user, what is the average rating that they are giving to movies. So let's use the average function, average of r.rating, and let's return that as average rating. So now we're not only bringing the username back, the number of movies they rated, and we can start to see whether they are a generally high reviewer or a generally low reviewer. You might start taking this into account with an advanced recommendation engine by saying, well, this user always gives 5 stars, so a 5-star review from this user doesn't really tell us much. Let's add one more column to this set of results. So we've got a username, we've got a count of the nodes, we've got an aggregation of a property on the relationship, and now let's add one aggregation of the properties on the movie nodes. Why don't we return the average of the IMDb rating of the movies they've watched? So average r.imdb rating as average IMDb. That seems to return all nulls, so let's check what we did there. We're returning r.imdb rating. Actually, it's not the relationship that has the IMDb rating, it's the movie that has the IMDb rating. So let's change that alias to m and rerun that query. We can see that although these ratings are on 2 different scales, user ratings from 1 to 5 and IMDb's from 1 to 10, it starts to give us an idea of how these users' ratings compare to the population. So this is just a few examples of how we can aggregate the data that we find in nodes, in relationship properties, and in node properties. Supposing my son has 3 favorite movies, Jumanji, Home Alone, and Aladdin. And the first thing he wants to know are all the actors related with each of those movies. So to start with, let's create a match statement to the first movie, which will give an alias m1. Obviously, it's a movie labeled node with title Jumanji. And we want to find the relationship to actor nodes. And in fact, let's give that the alias A1. Almost certainly these actors are not the ones that appear in those other movies, so I can't simply continue a relationship on the other side and find the other movie. Instead, what I can do is create a separate match statement. And this time I can just repeat the same syntax, change my alias to make sure I'm actually referring to a different movie, change the name, Home Alone, and I need to change the alias on the actor as well, otherwise I'm effectively referring and asking for the same actor. So A2, and we'll do the same one more time to match the third movie with A3, and where the title is Aladdin. So let's see what happens first of all when we return M1, M2, M3, A1, A2, and A3. So we actually get all of the actors related to each of those movies separately. And actually, we do have one common actor, Robin Williams, who appeared in both Jumanji and Aladdin. But now my son wants to know, well, what are all the other movies which all these actors appeared in? And so what we can do is we can just extend each of these sequences along to the movies that connect to those actors. So let's give this the alias OM1 for other movies, which also needs the movie label. We'll do the same for the second line. Again, we need a different alias to make sure they're not the same other movies. And then finally, OM3, again, label movie. So let's return OM1, OM2, OM3, and let's make sure we include a limit statement just to make sure our results don't get crazy. And so now based on 3 original movies, Aladdin, Jumanji, and Home Alone, we found the actors that acted in those films and the other movies that those actors appeared in. So now I can give this whole list back to my son and he can watch away. In the last video, we had a very specific starting point for our query. We had 3 movies that we were interested in, and then we were interested in a 2-hop relationship from there. But what if we don't know exactly what those nodes are going to be? So this time I'm interested in finding the top 5 rated movies. So simply by a count of ratings. And for each of those movies, I want to know which actors appeared in them. So let's start by finding these movie nodes that have a relationship with user nodes. And let's return m and the count of users as count ratings. Order by count ratings, descending, and let's limit that to 5. So I have an error there, which seems to be because I put a comma after count ratings. I don't need that. So this should give me my top 5 movies. And let's just return those as m.title for a second so that we can see the count for each one. So 341, 324, and so on. So we can see that Forrest Gump is the top rated movie in terms of number of ratings. And effectively, this now becomes our new starting point for our query. So we want to use any of these nodes as the start of our new pattern. It's kind of like a subquery in SQL. Let's just remove the title for a minute so we're going back to the nodes. Instead of returning these nodes, I want to continue the query with them. So let's swap return for with. I can still keep my order by and still keep my limit. But after I've done that, my query isn't going to stop and return results because I haven't yet included a return statement. This time I can go back into a second match statement. I can start with my alias m to refer to any of these nodes that have been limited to 5. I can refer to a new relationship to some actor nodes. And then I can return, for the final time, the 5 movie nodes and all their related actors. Let's limit these results to 50. And so this gives me a dynamic way to first search for the top number of nodes by some criteria, before then moving on to find a secondary relationship. This type of syntax makes Cypher incredibly easy to write these type of subqueries with, and really shortens the amount of code that we have to write. Now that you've got all the basic skills, you're ready to start answering some applied questions about our graph. In the student materials, you'll find this slide with a series of questions. Each question focuses on one of those key themes that we can use a graph for. So question 1 is about importance. Identify the most influential actors, measured by the total number of films they acted in. You've got a series of 7 different questions to work on, and each one of these can be answered with the knowledge you've gained in the previous chapter. I do very much encourage you, though, to have a go at each one before you look at the answers. This will really help you start to think about the graph and to start thinking independently. The first question I gave you was about importance. I wanted you to identify the most influential actors as measured by the total number of films they acted in. Let's take a look at how you would do that in Neo4j. So the first thing I'm going to do is create a simple query to find actor nodes that acted in movie nodes. And I'm going to return both A and M. Now I didn't put a limit on that, so it may take a few seconds to run. It doesn't return all the nodes, but it gives me a good sense of what's going on. It gives me all my actor nodes and all the films that they've worked on. The next step was to expand the query to return a list of names and then a count of those movie nodes instead. So I used the count function to count my M alias on movies. Obviously that's going to return a list, and I've ordered it by the count of movies in descending order. And that gives me this table with the actor who's worked on the most movies at the top, Robert De Niro. Now, that's a lot of movies, and how do I know if I've got the right answer? It might be worth me sense-checking one of those. So if I just scroll down a bit further and find an actor with a few less movies, here I've got Daniel Radcliffe, and we're saying he's acted in 10 movies. So let's just pull out another simple query and match the actor node with the name Daniel Radcliffe, find all the movie nodes that he acted in, and just return them visually. And we can see, sure enough, there are 10. So it seems like our table of results below is providing the correct results. And what we can say is the most influential actor, according to the number of movies, is Robert De Niro. Question 2, again, was about importance. Identify the most influential actors, but this time measured by the total number of other actors they worked with. Now, there's a couple of different ways we could do this one. Either we could create a match to find actor nodes that have a two-step relationship using the *2 notation to other actor nodes. And I'll just call these ones, and I'll just give these the alias B to differentiate them from my original list of actors. Again, we use the actor label, and let's try returning both A and B. And just to make sure we don't get too many results at this stage, let's just create a limit of 50. Now, because actors are not connected by a direct relationship, we're not seeing visually the lines between them. So before we try and summarize into a table, let's try and get to that visual layout. Instead of defining this relationship with a two-step hop, let's define a relationship to a movie node, which then has a relationship to the other actors. And now we can return A, M, and B. Now we see a better graphical representation that's showing us all the actors and how they are connected to the other actors they've worked with. So now let's change that return clause to bring back each actor's name and a count of the B nodes, which represent the actors that they worked with, and we'll return that as count colleagues. Let's order these results by count colleagues descending, and we'll leave the limit of 50 there. So this is saying that Clint Eastwood has worked with 262 other actors. You could definitely argue that this is the correct result. After all, the question was, identify the most influential actors measured by the total number of other actors they worked with. Now again, there's a little ambiguity here in the question. What if they worked with the same actor twice, but on two different movies? Does that actor count more than once? Looking back at our patterns, this pattern may be detected twice between the same pair of actors, but via a different movie. And so one final optional step we can add to this query is to return a count of distinct actors that they have worked with. So we can place that inside the count and use the distinct B to return a unique set of colleagues that they have worked with. So Robert De Niro is in fact top of the list with 158 unique actor colleagues. And so we've actually changed the top results by changing the definition. So that's just a reminder to always be absolutely clear with your stakeholders. What exactly are they looking for in the question? Are the measures clear, and do you both have the same understanding of what the measure means? Okay, question 3, and this one is about connection. Find the connection between Clint Eastwood and Morgan Freeman. How do these people know each other, and what did they work on together? You can imagine this example being extended to LinkedIn or something. If I want to connect with a friend of a friend, who should I ask to introduce me? Or in a fraud case, we might be thinking about how do these people know each other? Let's answer this one in Neo4j. So similar to the last query, I've actually got two separate actor nodes. The first one I've given the alias A1, the label is actor, and I've set the property restriction that the name must be Clint Eastwood. I've done the same thing for Morgan Freeman as an A2 actor node. As we know, this isn't going to give us any results because they don't have a single direct relationship. What we need to introduce is a movie node in the middle. So M, movie, and that second relationship. And we want to return A1, we want to return the movie that they worked on together, and we want to return A2. And so really M here are going to be the movie nodes that show us how these two people are connected. Here we can see there are 3 movies that Morgan Freeman and Clint Eastwood have worked on together. So those are the common connection. Question 4. Find the average rating of movies that Clint Eastwood and Morgan Freeman worked on together. So this one's going to be about aggregation, and we can actually start with the query that we wrote for the last question. And we just need to change slightly what we want to return. We're already finding the right pattern. Movies that Clint Eastwood and Morgan Freeman have worked on together. But we can replace the return line with the average IMDb rating of the movie nodes. And so that gives us an answer of 8.04 with a lot of decimal places. Let's tidy that up by instead returning a rounded answer. Round this number to, let's say, 2 decimal places. And so we get 8.04. So the average rating of movies that these 2 actors worked on together, as far as IMDb is concerned, is 8.04. So here's an example where we're aggregating the properties of these connecting nodes, the 3 movies in the middle. When we were thinking of that example of who should we ask to introduce us, maybe if there's 4 different options, the next step is to assess, well, what's the average response time of these users? And so between the 4, we would recommend the one that has the lowest average response time. Question 5. Okay, this time we forget Morgan Freeman, and we're simply finding the actor with which Clint Eastwood had the highest IMDb rating. So just to phrase that a slightly different way, we're going to find all of the actors that Clint Eastwood worked with, and for each one, we'll take the average of IMDb ratings of the movies they worked on together. If that's not 100% clear, it'll make sense once we write this query. And again, we can extend the query from the last question. Let's bring that up one level. We still want this A1 actor node, we still want the movie, and we still want the A2 actor node, but this time we want to remove that restriction of Morgan Freeman. It can be any actor that Clint Eastwood worked with. At the moment, this query will simply return the average IMDb rating of all of the movies that Clint Eastwood worked on with other actors. But we want to know that average by colleague. So we can add one more thing to the return statement, which is simply A2, the colleague actor node. So return a list of the colleague actor nodes, and for each one, return the average IMDb ratings of the movie nodes that connect them. Now, I actually meant to return a table of results here, and the reason it didn't was because I returned A2, which represents the node itself, whereas I actually want A2.name. I wanted the name property. That returns my list of actors, and we can just add an order by statement here to rank these results, IMDb rating desk. And so to answer the question, Clint Eastwood worked with many different actors, but the one that he got the highest average IMDb rating with was Eli Wallach. Question 6. Find out which actors Clint Eastwood has worked with on multiple films. For each of those actors, how many films have they worked on? And so I can start by creating a pattern that matches an actor node A1 with name Clint Eastwood with a movie and across to an actor. And for each one of those matching other actors, A2, I want to return the name. I also want to return a count of unique movies that they work together on. So count distinct M, and let's return that as count movies. Order the results by count movies, descending, and let's limit those to 50. And so we can see that Clint Eastwood worked with Sondra Locke on 6 movies. If you're wondering why Clint Eastwood himself appears in these results, let's take a look at the results in a different way. Let's return A2, A1, and M, and limit that to 50 instead. So Clint Eastwood appears at the center of this results graph. And we can see that in a lot of cases, he both directed and acted in the same movie. So the pattern that we're matching is going from Clint Eastwood node in the middle to the movie, and then back to Clint Eastwood down the other relationship. We haven't specified a direction for the relationship, so we can travel either way. So to remove Clint from the results, we could simply add one more line, which is where A2 dot name does not equal Clint Eastwood. Now, when we return our list instead and order by count movies descending, we no longer get Clint Eastwood appearing at the top. Question 7. Find all people that both directed and acted in the same movie. And so this is an example of affinity where we're searching for the same pattern at multiple points in our graph. This one's an interesting one to solve, as we have to reference our person node multiple times. Ideally, what we would write is a match statement to find persons that have a relationship of type acted in and directed. But as you saw in that other video, we don't have a way of combining 2 labels in a relationship. We can use the pipe to represent or, but we don't have a way of doing and. So instead, we have to reference the movie node, and then as a separate relationship, we have to create this directed relationship. But we still want that directed relationship to refer back to the same person node. And because we're referring to the same person node, we can use the same alias. So that tells the pattern that this must be the same node as the one that we found at the start. If we then simply return P and M, we should get all examples where a person has taken on those 2 roles within a film.